exist. Once again, I started the lesson too late. The limit does not exist, so f prime at 1 does not exist. If I zoomed in tight enough on that, it's never going to be locally linear. It's always going to have this, in fact, it'll be even more abrupt, that change in slope. All right, is that going okay, those type? Okay. Before I get into the lesson, there was a question on set 80, number 17, that I meant to go over when I handed it back. I think I handed it back. And you can get it out or not, it's up to you. Some people did this right, but the majority did it wrong. And that's that. Am I right in saying I gave you set 80, number 17? Okay, 17C. Part C, set 80, 17C. Now, the one before it went fine because it didn't require any in-depth thought on your part. What was the one before it? The derivative with respect to x of what integral? Like, give me A, actually, please. The integral from where to where? 3 to x of 2t minus 2. Now, I could most definitely integrate this, substitute, and then differentiate, but most people saw this as a shortcut. The derivative or the antiderivative is just the function. And for that problem, it is that easy. That's true. That's good. However, when you get one like part C, things get a little more complicated. I'm going to show you a ton of work working towards how you could do it without all the work, but I want you to know why, not just throw it at you. All right, so if I were to do this, I would have 3 things to do. Anti-differentiate, evaluate, and differentiate, right? You work it out, inside out. So if I were to take the antiderivative, it's t squared minus 2t. Yeah? If I were to evaluate it at upper minus lower, it would be sine squared minus 2 sine x, that quantity minus 3 squared minus 2 times 3 or 6. Then, if I differentiate, when I differentiate here, what's the derivative of sine squared? 2 sine of x, cosine of x. What's the derivative of 2 sine of x? 2 cosine of x. And what's the derivative of all that constant? 0. Now, that said then, this is 2 sine of x minus 2 times cosine of x. Our shortcut then, can I just say, oh, when you do this, it's just these two cancel each other out, and you throw the sine in there? Well, no, there's a little more to it than that. There's a chain rule component to this. It's, yes, this goes in, but then if this is a function, you then have to follow by taking the derivative of that function. That's that cosine. There's a chain rule component to that. Are you with me? Okay. That is called the second part of the fundamental theorem of calculus. The idea that the derivative and the antiderivative are inverses. We will come back to that later, but just wanted to touch on it now. The lesson. Here we go. Logarithmic differentiation. That sounds wordy and smart. Don't you feel smart just learning logarithmic differentiation? Yeah. You should say that, and you'll impress the guys or the girls. They'll be use that for a pickup line in the bar. I know logarithmic differentiation now. It works every time. Okay. Do you recall how we differentiated or found the derivative of y equals 2 to the x? How do we do it? You took the natural log of both sides. And was that just to further complicate the issue, or did that achieve some goal? What did that achieve? What did that do for us? It allowed you to bring that x down. That is the name of the game. Log allows you to bring the exponent down. And anytime you have this thorny issue of having a log in the exponent, or an exponent, a variable in the exponent, you should consider that as an option. Okay? Up to that point, we hadn't done any calculus. That was just pre-calculus or log work. Now we take the derivative implicitly. The derivative of the left being 1 over y dy dx equals log of 2, yay? So dy dx is y times the log of 2. But we then finished by substituting back in for y and saying dy dx is 2 the x times the log of 2. We then started to memorize the shortcut and not do all that. Now, we are going to go back and use that work again on problems that are similar but a little more complicated. That's a little more complicated because now the base is a variable power and the exponent. But the idea is still the same. By the way, that's one of the most powerful functions in the world. The base and the exponent are growing. It's more powerful than exponential. What should you do if you want to take the derivative? You do what? Natural log of both sides. Natural log of y equals x log of x. I'm not showing bringing the variable exponent down step, but you get the idea. Now differentiate. The differential or the derivative of the left is 1 over y, dy dx, and the right side product rule derivative. What do you get? Yes. Something like 1 plus natural log of x when it's all cleaned up, yeah? And so dy dx, with moving the y back and substituting in the same step, our derivative is x to the x times the sum 1 plus log of x. Sweet. All right. Now then, things get more complicated, but that should get you going. Go. I think we didn't have enough room for that one, so we'll just scratch that one and do the first 3. We'll talk in a little bit after you've had a chance to rest, please. Don't put your math amigos. Amigo, help me. How'd you do in the first? Good? Okay. Before you get too far into it, can I just say about the first one? But I try and take data on every single question I ever give on a test or a quiz, and I figure out what percentage of the people missed every question. The first time I taught this class, I phrased the question like this: the success rate was 95% success. The second, or actually more like the 4th or 5th year, I gave the question that way, success rate less than half. Why is that so much harder? Because what? Yeah, the whole idea is predicated on the log of both sides of an equation. This isn't an equation, it's an expression. So what should you do? Make an equation. You make an equation, you say let y equal u to the cotangent of u so that you can use this law of vector. So if it doesn't come as an equation, make it an equation. Last one is a humdinger, yeah? On the third one, do you just mindlessly plow ahead and log both sides? You do not? I think the way I phrased that question is probably no. No. The reason is that that exponential is not your first issue. Your first issue is the chain rule / outside rule. The inner derivative doesn't come till later. So, what would you do? Yeah, let's start. We will worry about that later. Right now, we'll worry about the chain rule. What's the derivative of the outer function? Secant squared of x to the 3x squared, then times the derivative of x to the 3x squared. Now that, then I'm going to compartmentalize, break this into little pieces. They're more manageable. That, I would go off to the side and create a little equation and do that logarithmic differentiation style. So something like let y equal x to the 3x squared. Find the derivative on that. Now find the derivative on that little piece. Like that. What do you think? All right. So that had a little chain rule, and if you have a log problem within a bigger problem, then go off to the side and treat a little compartment. Are you with me? So One rule or one use of logarithmic differentiation is when you have a function, what? What are these cases? When are we using this? When we have a exponent that's a function or an x or something, right? All right. There's actually a second use of logarithmic differentiation, and that's to avoid the worst derivatives of all time. If I gave you this function and I said differentiate it, you would have a quotient rule with a product rule with two chain rules minus a product rule with chain rules over the denominator squared. So in other words, I have two products, two chains, and a quotient. Pretty gross, yeah? Now, with logs, you can make it a little easier before you take the derivative. Why would taking a log of both sides help you? What would that do besides seemingly make it more complicated? Yeah, that allows you to split it into many manageable derivatives. Now, don't touch the left side because we're not ready to differentiate it. Just keep it the same. Now the right side. So what's the cleanest possible way to write the right side? Let's start with this guy. 1/2 log x minus 2. If I thought of the root as a power and brought the power down, pretty clean, right? And then what? Plus the log of, now that one it doesn't really have one big power, so I can't do that power thing there. Okay, the other term's in the denominator, so then what do? Minus the log of r minus x in minus the log of sine of x. Now, I've done a lot of work, but I haven't actually done any differentiating. Now let's take the derivative. What's the derivative of the left side? 1 over y dy dx equals 1 over 3 times the x minus 2 difference plus chain rule 4x over 2x squared plus 1 minus chain rule -1 over 4 minus x minus chain rule cosine of x over sine of x. All right, last but not least, move over and sub back. These will sometimes take all the way across the paper, so I'll usually make these boxes one wide box, but here's the say. All right, so when I move y over, it gets subbed back with that big, whole, terrible thing that we started with. That represents the move back y. Then we start to write our derivative on the right-hand side, maybe cleaning up a little as we go. 1 over 2 with x minus 2 is fine. 4x over 2x squared plus 1 is fine. I might call the next term plus 1 over 4 minus x, combining your two negatives. And then maybe minus cotangents. And there's your derivative. You get the gist? Okay, try number 9 on your paper, which I'll put up for you right here. 9 is take the derivative of number 9 is take the derivative of y equals root x minus 1 x cubed minus 1 sine of x all over x squared plus 1 x to the 4th plus 1. Find y dx. I gave you number 9 to do, right? I didn't scratch that off. Right? Feel free to do a little combining of steps. I was showing everything in your notes. probably consider the expansion a good first step. And then maybe we could go, what do you think? Could we go straight to the derivative? We'll take the derivative and move the y over in one. Surely that's cool, isn't it? Is that what you're getting? Yes? Okay, good deal. So, here we go. Should we go to last night's homework? All right, here we go. So, hyperbolic trig. Yay. Hyperbolic trig. So let's talk about this real quick. First of all, what the heck, why even do this? Why would you just throw some exponentials together? Just for fun? And the answer is no, because there were certain problems that couldn't be done. Let me give you this here an example. Okay? If I hang a slack curve from 2 points, what's the math shape of that? Feels like parabola, right? It's not. The problem is that the growth is too steep on the outside. It grows faster than parabola. And so as much as people, including Galileo, tried to fit a parabola equation to this, it didn't work. And then, therefore, trying to find the length of this. Now, finding arc length is a huge idea of calculus that we'll do second semester. It goes to millions of little calculations. It's super cool. But it's hard to find the arc length of this if the equation on which you're basing it isn't right or isn't accurate. And this parabola is a decent model, but not perfect. So they needed something that grows quicker on the outsides. And one thing that grows really quick is exponentials, yeah. So they start playing with this, and it's about 1700s. It was after the invention of the calculus, but still in its infancy, and they're talking about how we can match this curve. Now that's the genesis of this hyperbolic idea, okay? First, did you show this to be true okay in this proofy area? Did that go okay? Okay, if you would like me to show that, I can show that. But the one, besides this main identity, if you were to take this identity and divide by cosh squared each place, then you'd get another main Pythagorean identity, which is 1 minus hyperbolic tangent. You say tangent if you like. Just please don't say that in college and say I was your teacher. Okay? Just keep it to yourself, or say you were self-taught. Because I don't want my name attached to yours. You're embarrassing me. All right. 1 minus tangent, hyperbolic tangent squared is obviously my little diatribe did no good whatsoever because you're still saying so. Okay, fine. All right. So that's one. The other one is if you divide through by sinh. Now, Carver, Miss Emily Carver said, why sinh? I don't even see it. Where's the C? Why sinh? Why isn't it simcha? Or, you got me? I don't know why not simcha, other than it sounds really weird. But you're right, there's no ch in there. Whatever, it is what it is. I'm not trying to improve on the math. I'm just going with it. Cos squared, so this is minus. Cos squared minus 1 is what? Sorry, not cos. Sorry. Cos, no wonder. Hyperbolic cotangent squared minus 1 equals hyperbolic cosecant squared. Or quiche, as they called it. Quiche, whatever. It's not quiche. I've never heard that before. All right. Now, if you make into the substitution or into the big identity for normal trig, sine squared plus cosine squared equals 1, if you were to substitute x equals cosine, now, this actually makes a good deal of sense. In the unit circle, isn't the x side the adjacent side? So that's not just out of the blue. It makes sense to make x cosine. In the unit circle, the hypotenuse is, I'm asking you to say this, 1. And so it makes sense that the cosine of an angle would be x. That's not just kind of out of the blue. But when you make those substitutions, you get y squared plus x squared equals 1, which is a unit circle, yeah? Now, because there's a lot of similarities to trig, they said, well, what if you do that same idea for this identity? If you let x equal cos, then you get something like x squared minus y squared equals 1, which is not a circle, but a hyperbola. In fact, it's called a unit hyperbola. All right, now the picture of that, the x and the y in that are not as awesome. But would you write yourself a note here, please? When you do sinh of something or cos of something or any other else, there is no angle. Does not involve angles. Sine and cosine are exponential. It's not about when the angle is this, the opposite side. There's no trig-sine ratio here. There's a lot of overlap to trig, but they're not trig-based, angle-based stuff. So if you put sine of 2 in your, or hyperbolic sine of 2 in your calculator, punched it, then put your calculator in degrees and put hyperbolic sine of 2, nothing would happen. They would be exactly the same, because radians and degrees mean nothing for hyperbolic trig. There's no angle. All right, 2 is more like the exponent in the expression. What you put into the function isn't an angle. It's just some kind of exponent. All right, so keep that in mind. It's got a lot of trig similarities, but it's not trig. Other connections. The hyperbolic tangent is the same as normal in that it's defined as sine over cosine. Hyperbolic cotangent is hyperbolic or cos over sinh. Hyperbolic secant or secant is, or sech, whatever, not, is 1 over cos. And hyperbolic cosecant is 1 over sinh. Okay? There are also inverses. Now, all these good stuff, this good stuff is useful for life. Let's talk about the hierarchy of functions here. The greatest in all of math functions is linear. It's the king of all functions. It's more important than any other. It's the one that happens most in life, a linear relationship. Every proportion you ever saw is linear. I mean, if I do 2 cups of sugar to whatever 5 cookies, that's linear. Every proportion is linear, and linear is the big daddy of all functions. After that, the 2 big functions for mathematics are polynomial or algebraic functions, where you're talking, polynomials, x squared, square root of x, all those super important, motion and all that good stuff. And then what's called the transcendental functions, e to the x, log, sine, cosine, all the trig functions, those are called transcendental functions, all right? Those are the biggest part of all of mathematics. Now, these then would you consider transcendental, but a little lesser. These are somewhere comparable to absolute value and piecewise. They're not big daddies, but they're important and they're useful to have. And then the garbage functions like the greatest integer function and all that stuff you learned, that they're useful in very rare cases. That, you know, the modulus function, they're lesser functions. Okay, so these are important more so in upper math. You can integrate a ton of things if you know hyperbolic trig. So it'll allow you to integrate stuff. I will also say this before I go on. This is not on the AP exam. It is, however, part of every college calculus course I ever saw. I have no idea why it's not on the AP exam, but you cannot go to college and take Calc 3 without having seen this. You would be a major disadvantage, right? So it's important that you at least have some familiarity. Did you get these in your calculator okay? Good. What was cinch of 2? 3 point what? 760? No. 3.627. It might not actually shock you, but I have hearing aids. I just don't use them. They don't work very well. Anyway, I should try and use the hyperbolic sine inverse of 2. What was it? 1.444. Okay. All right. The Inspire, the easiest way to go back is to go back and use an aids on that. I hope you were able to find that. Okay. Let's go to the graphs. This goes to the main reason these were started. I think you should be able to graph these without a calculator, just by using your noggin and then putting two functions together. So this is the thought process. I'll also say this, again, for college, it's not often that you're going to find a college course where you can use your graphing calculator on exams, at least. You need to be able to do stuff like this without a calculator. They're less calculator-driven in college than they are in high school. E to the x over 2. We know e to the x looks like this. What does the 1/2 do to the curve? What does it do to the y-intercept? It makes the y-intercept 1/2 now instead. It's still going to grow quickly. Exponential is still going to dominate the 1/2, but it's going to just be a little less quickly growing. E to the negative x over 2, that's exponential decay instead. It has the same y-intercept, but it's going to decay over here and grow over here. You follow? All right then, let's put those two ideas together. This would be the thought process. If I were going to graph this, I wouldn't say, oh my God, that looks so hard. You just think, all right, I know what e to the x over 2 looks like, and I know what e to the negative x over 2 looks like. What happens if I put them together? You're just going to look at left side, y-axis, right side. On the left side, I'm taking the e curve and subtracting the e to the negative. Now that means taking the green curve minus the blue curve. Small positives minus big positives. Give you small positives minus huge positives. Give you big negatives. So it'll be down here. At the axis, 1/2 minus 1/2 is 0. And now I'm talking big positives minus small positives. That's big positives, okay? I know it feels like a cube, but it's exponential. It's much steeper than a cube. Any cube. I could graph a trillion x cubed on top of that, and that would eventually overtake it. It would grow faster eventually, all right? What about this one then? On the left-hand side, I'm adding the two. So I'm taking big positives plus small positives. I get big positives still. 1/2 plus 1/2 is 1. And then big positives plus small positives is big positives. Now again, that looks like a parabola. It's not. It's very, very steep. This, please, would you zoom in on this and write yourself a note? That's called the catenary curve. That is a big reason why hyperbolic trig was invented. It is the shape of any slack cable with weight to it, any significant weight to it anyway. So any, like a telephone wire, if you put a telephone wire between two posts, this is the curve that models it. Whether you know it or not, the St. Louis arch, hyperbolic trig. It's not a parabola. It's actually a Cauchy curve. The St. Louis arch is a hyperbolic trig. At any rate, it's an important calculation in physics and engineering. We'll go through a lot of the calculus of it second semester. Okay, moving on. So this one was fun. In that fifth period, they said, oh, that goes to infinity and that goes to infinity. And so they used L'Hopital. Now, this is where I started to have my fun. Because when they did L'Hopital, their first derivative was e to the x plus e to the negative x over e to the x minus e to the negative x, yeah? Now that's still L'Hopital, so they did it again. And when they did it again, they got e to the x minus e to the negative x over e to the x plus e to the negative x. Now, at that point, I thought, oh, they'll see that that looks familiar. Nope. Kept on plowing ahead. They are right back to where they started, but they kept on doing L'Hopital a third time. That blew my mind. Okay? Open your eyes. So you can do L'Hopital on this the livelong day until you die, and you still won't have an answer. At some point, you're going to have to think of it a different way, and it goes a little like this. As x goes to positive infinity, isn't this a huge positive? And this, what is this? This is a minus a small positive, practically zero, right? Small positive, huge positive, plus small positive. In the end, then, the small positives are a non-issue. It's huge positive over a huge positive. Now, that could be indeterminate if the functions weren't the same. They're the same, and so they would approach 1. Okay. This one, also 1, or not quite? Not quite, because this is, now that it's going to negative infinity, this would be more like 0 minus huge positive over 0 plus huge positive. That's not going to approach 1. That's going to approach negative. So the end behavior for inverse tangent looks like that. Now, that's good for you to see because you think that all horizontal asymptotes are the same on both sides. That's not true. There are many functions that have horizontal asymptotes that are different for positive and negative infinity. That's why you really should always take both sides when you do end behavior, not just one, because it can be different. What about at 0? What does it approach? 0. And so the hyperbolic tangent function looks like that. Differentiating. What was your derivative of sinh? Cosh. What's your derivative of cosh? Negative sinh? No, just sinh. No negative. Like your normal trig. It's just normal positive. What about the other 4? The derivative of tangent, hyperbolic tangent, is it secant squared like we would expect? It wasn't? I think it was. I got that it was secant, hyperbolic secant squared. We did not agree? We get it, see, Claire and I agree. Okay? Now, you will see that all 3 of these, what I would consider all 3 of these normal ones, they're all positive. The reciprocals, all negative. So, for example, the derivative of, let's go secant, hyperbolic secant. Normal trig, it's secant tangent. Or for hyperbolic trig, it's negative secant tangent hyperbolic. Negative. The derivative for hyperbolic cotangent. What was it? Is it normal negative cosecant? Yeah, it is. It's negative. Hyperbolic cosecant. And the derivative of hyperbolic cosecant is negative cosecant cotangent. Checkity check. Okay, the antiderivatives then. What's the antiderivative of sinh? Cosh plus c. What's the antiderivative of cosh? Sinh plus c. Tangent. How do you do that? That's a process, not just a fact. U sub, it's sinh over cosh. U sub it, and did you get something like the natural log of the absolute value of cosh plus c? Yeah? And then the last one. Sorry, I guess I thought it was going to be clear when I put this approximation on there, but I didn't intend for you to try and anti-differentiate that. It is a calculator question. So what did you get? 2.762. What is the antiderivative of that? Well, you are clear. You know this, but I think you know this, but it's better. Does everything have an antiderivative? Can everything be anti-differentiated? No. I mean, this, for example, I could look for something that has that as a derivative all day long. You will never find it. There is nothing that has that as a derivative. Nothing. Okay. So not everything has a derivative. That's a large reason why you do series, because with a series, you can do that question, or at least get it as close as you want it with an infinite series. So that's a big part of Calc 2. All right, dealing with those can't be integrated cases. That's it. Now, when I go over a whole fun sheet like we just did, I don't feel like it's necessary to collect this. You would have to be a real weasel to not have this done now, right? I mean, we just went over the whole thing. Do you agree? So if you are a real weasel who's honest, come see me and say, I didn't do this. Give me the 0. But otherwise, I am going to just put you down for a 10 and you keep it, okay? Feel free to put a 10 on yours and a little smiley face. I don't do that. So whatever you want. Okay? The rest of the time is yours. Sorry, it's not much time. Yes? Yeah, this is what we used to wear back in the 80s. We would wear cloth. I saw this at Google and I said, I gotta have that. I got 75 cents. Yeah. It's a piece. And it's super useful as a rope. Yeah, added bonus. No.